So today we're looking to have Ankit Barik, who's at Johns Hopkins University. So he did his PhD with Johannes Vicht, working on spherical co-wet flow and essentially inertial modes in differentially rotating flows. Was part of that. And since then has been working on a number of different things, particularly using the magic code. And I think today we're talking about a different code, looking at properties of rotating convection in spherical shells.
Thank you very much for the invitation. Today I'll talk about, as Adrian mentioned, not magic, despite that being the main code I use, but today I'll talk about linear code, where we have used it to study the onset of convection in rotating spherical shells, and in particular the variations with the radius ratio, the aspect ratio of the shell. How do things change? Now, of course, for this audience, convection, I don't have to explain why convection is important, probably, but we know that convection drives heat transport and dynamics. It can drive dynamos, and it can occur in a massive range of spherical geometries, from liquid cores of planets to magma oceans, atmospheres, subsurface oceans, and so on. However, if you're modeling fluid dynamics and dynamos in a rotating spherical shell, it's sort of useful to know where in the parameter space you are, in the sense how supercritical you are. So in that sense, it's useful to understand the linear problem and figure out where the critical onset of convection takes place. There is a classic fluid dynamics problem where you have where you have a spherical shell, and the sphere inside is hot and the sphere outside is cold, and they're rotating at a rate omega. And this has been studied since even before Chandrasekhar, but one of the first complete studies was done by him. And then there have been several subsequent theoretical studies and even an experimental one. In the 2000s, these two studies came out, which really provided a nice global stability analysis, which could quantitatively predict onset of convection in a really nice way. But then, so the first one by Chris Jones and others in 2000 focused on a rapidly rotating sphere, not a shell. And the one in 2004 by Dormy et al. Focused on rotating spherical shells, and they mostly looked at one example of a thick shell and one of a thin shell. But even though the theory essentially reduced the problem to a 1D differential equation, it still required some numerical effort to solve that equation and then figure out all the other parameters associated with it and so on. And so even numerically, there has been very limited parameter sweeps in shell geometry to check systematically how things change when you make the shell go from a very thick shell to a very thin shell. What happens? So that was the idea that so this was a project born out of me and John Arnold just talking about different things and magma oceans and so on. And he said, you know, why don't we look at how things change when you make the shell go from very thick to very thin? And so we just started looking at that. And we thought, why not create a general database of critical quantities and make it available to the community? So that was the main, and that's the main aim and scope of the study, to sort of look at in more of an overview way how the critical quantities associated with convection onset vary with shell thickness and rotation rate, and to create this huge database that we created of relevant critical parameters, and to just make it available to the community so they can more or less just look it up instead of having to run actual eigenvalue codes and so on. And in the process, we try to find if we can find simple sort of thumb rules or fits to the parameters we have that can predict critical quantities reasonably well. So this is our setup. We used fixed temperature boundary conditions at both boundaries. In future, we want to, of course, explore fixed flux as well. But as a starting point, we go with fixed temperature. And the equilibrium is hydrostatic. And with fixed temperature, you get this nice adiabatic profile that goes as 1/r squared. And so these two shells are held, these two boundaries are held fixed at Ti and Tl, and they're rotating with omega. And you solve for perturbations around them. So you have U, that's velocity, theta is temperature, P is pressure, which we eventually get rid of, as I will tell you in a few of some of the following slides. And they all vary with an azimuthal wave number m, phi, and time dependence lambda, where the real part gives you the growth or decay rate, and the imaginary part gives you the drift frequency. Now, once you write that out, using these scaling, so we use the gap width as length scale, rotation rate as inverse of rotation rate as the unit of time, and the temperature contrast as the temperature scale. And then you end up with these sets of familiar equations, the Navier-Stokes, and the heat equation. And we use no slip and fixed temperature boundary conditions. So scaling equations this way brings out the important non-dimensional parameters that we would look at. First is the radius ratio. So we go all the way from 0.05, so very thick shell, we denote the radius ratio by chi, and all the way to 0.95, so very, very thin shell. And of course, in real astrophysical objects, this is highly varied as well. The Ekman number, which gives the ratio of viscosity to viscous drag to Coriolis force, that usually varies from somewhere around 10 raised to the power minus 10 to 10 raised to the power minus 15 in astrophysical bodies. Can probably go lower if it's really rapidly rotating. In our study, we go down to 10 raised to the minus 9 for an Earth-like geometry, and minus 7 for all other in all other cases. The Prandtl number, which is the ratio of momentum diffusion or viscosity to thermal diffusivity, and that's held at 1. And of course, in real bodies, it can go down pretty low. And the Rayleigh number, which is a measure of the thermal driving, that's the one to be determined, the critical that determines the critical onset. Now we use a spectral method, so it's fully spectral. So the first idea is you get rid of pressure by taking the curl of Navier-Stokes, and you have two remaining variables, and once you decompose velocity in polaritoidal form, four remaining variables because you have three components, and then that reduces to three variables. WZ, which is the polaritoidal, and the temperature. Apologies for the same theta. This is why you should not change notations in the middle of preparing the talk. Anyway, so we use spherical harmonic expansion in the angular direction, and in the radial direction we use Gegenbauer polynomials, and this is a beautiful paper by Oliver and Townsend in 2013, which nicely described the numerical method of using this radial of using Gegenbauer polynomials as an expansion in radius. And this expansion produces sparse matrices, which then significantly reduce the memory requirement. So and then that allows us to go down fairly low in Ekman number and so on. And so the resultant problem, once you implement this expansion, is a generalized eigenvalue problem. And then you solve for the eigenvalue, which gives you the growth rate, and then you get your eigenvector coefficients. So the problem is solved using the slep-C library, which is fairly fast, and that also makes the code fairly nice and easy to use. So you can go down to extreme parameters without running into memory crunches, and then it can be solved fairly efficiently using slep-C. The code that sets it up all and solves the problem is called Cori. That's the code we use. It's another name for Persephone, daughter of Demeter and Zeus, and queen of the underworld. So it's a fairly apt name. And so during this study, we added the heat equation. And now the code can compute eigenvalues of a whole combination, Navier-Stokes equation, magnetic induction equation, as well as heat. And I've also managed to implement chemical transport in this. So you can go full double diffusive and MHD as well. There are several authors of the code. I particularly implemented convection part and visualization. Searching for critical parameters is a standard exercise where you fix one Ekman number and radius ratio, and then you basically provide an initial guess for a Rayleigh number, and then you search around it, do a sort of bisection search to find where does the growth rate go to 0. So an example is shown here where you start with the initial guess and the code searches around and finds, it searches in log space and finds another Rayleigh number where the growth rate has opposite sign, and once those two bounds are found, you you slowly converge where the growth rate goes to 0, and that's where you find the critical Rayleigh number up to whatever tolerance you provide. And then, of course, for each wave number that you fix, you get different Rayleigh numbers, and then you choose the minimum and get the absolute critical. Now, an overview of the solutions. As you can see, when you have a really thick shell, you have nice, sort of nice, very spirally solutions with low wave numbers. And once you go down in Ekman or go to a thinner shell, you go to higher wave numbers, and sort of the spiraling nature sort of decreases, and to the more thinner shells you go, and they become more and more straight. I shouldn't say straight, they sort of unwrap and become more oriented in more radial direction. And so that's how the solutions look like, and this the colors show radial flow here in the equatorial plane. And so if you look at the full survey of solutions, our first stop is the critical wave number at onset, and the critical wave number increases steadily as you go to thinner and thinner shells, and also increases as expected as you go to lower and lower Ekman numbers, shown by the consecutively brighter lines. The next stop is the critical Rayleigh number, where as you go to more and more thin shells, the critical Rayleigh number goes down. It becomes actually smaller, and as you decrease the Ekman number, it goes up, which is well known. Rotation inhibits convection. And lastly, this is the critical drift frequency, which has a peculiar variation where it actually increases to a certain value for moderate shell thicknesses, and then decreases on both sides for thick and thin shells. Now we come back to simple, very first order scalings from linear theory. And that's how that's how they look like. So critical wave number is supposed to go as Ekman minus 1/3, critical Rayleigh number is Ekman minus 4/3, and the critical drift frequency is Ekman 1/3 when you scale time with the rotation rate. Now we first look at the critical wave number. Now that's how all the results look like, and now let's see how they collapse when we do the very first when we compensate with the very first order scaling. So once we compensate with the minus 1/3 scaling, everything nicely collapses down to a single curve. And since they do that, we thought, why don't we try to determine the equation of this curve? Now the basic idea for the variation of critical wave number like this is that a larger inner core can accommodate more number of convective columns. So the convective rules, they are always attached to the tangent cylinder, and then at a given Ekman number, a larger inner sphere gives rise to a large number of convection rows. And so one can argue that it's just simply proportional to the circumference of the inner sphere at the equator. And then we get the Ekman scaling here nicely anyway. And then there's some proportionality constant here, which is potentially a function of Ekman and the radius ratio. And if we break that down into our scaling, that's where the radius ratio goes in. And that works out nicely. If we take the ratio of these two, then we get, then it turns out it's nearly a constant. And to determine the constant, we perform a least square fit, and we obtain this sort of nice nice fit, or I like to call it a thumb rule, which can predict your critical wave number reasonably well. So how well does it do? So we've selected a few random Ekman numbers and radius ratios, and you can see that this is the actual value computed by eigenvalue computations, and this is just a predicted value. And from our simple thumb rule. And you can see in most cases they're fairly close, and close enough anyway for most practical purposes. Now we move on to the critical Rayleigh number. The critical Rayleigh number has sort of these S-shaped curves where they constantly decrease as you make the shell thinner and thinner. And once you compensate with the Ekman minus 4/3 scaling, they collapse much better for thinner shells than for thicker shells, which seen in a different way with the Ekman number on the x-axis and the compensated scaling on the y-axis. You can see that the thinner shells asymptote much quicker than the thicker shells. And the white line here shows the case for an Earth-like geometry where we have continued our computations down to 10⁻⁹, and you can see it's now sort of approaching an asymptotic value. Finally, the critical drift frequency, where it has this, as I said, this Euclidean nature of increasing for moderate shell thicknesses and then decreasing on either side. Once you compensate with the leading order asymptotic scaling, you obtain this sort of fairly nice collapse for all different shell thicknesses. There is a non-monotonous nature that's reflected here, but you can see they're all sort of almost nicely going towards an asymptote. Right. Now, finally, we thought, why not compare against actual asymptotic theory? So Dormy et al. 2004 gives considers only one case for differential heating, and no slip. Well, they consider no slip and free slip boundaries in all cases, but for differential heating, they only consider one shell thickness, and so they actually provide some values which we can use and plot, and they match up very nicely with our results, all the way down to they start matching very closely on 10 raised to the power minus 5, and they go all the way down to 10 raised to the power minus 9. And finally, we look at the nature of the solutions as well. So we look at if you take an equatorial cut and do an azimuthal average of the flow velocity, and then look at the radial flow and that its dependence on the cylindrical radius, and then you get these nice curves which line up very well with Dormy's airy function solution. So it all works out real well. Now you must be asking the question, okay, so what's the use of doing all of this? The idea is to, as I said in the beginning, to make this sort of database available to the community, whereby you can get your critical Rayleigh number, and because we have such a dense coverage in radius ratio, you can get your critical Rayleigh number and wave number at almost any desired radius ratio. Many people still run dynamo simulations at Ekman 10 raised to the power minus 4 or so. So if you're trying to get run dynamo simulations at minus 5 or minus 4, asymptotics are not going to help you, but our database can easily just give you an answer in a few seconds without having to solve any actual code or write or solve any actual code. And so we will make this database and an associated Jupyter notebook available to openly, so people can just use it to get their critical quantities. And so when the next time they run their simulations, they know where in the parameter space they are. So this table gives sort of these test predictions for values that are not in the database. And then we obtain the critical wave number by actual eigenvalue computations. And then the MC star is the ones we obtain through just straight interpolation. The double star is the one we obtain from our simple thumb rule, and they all agree fairly well. The same goes for critical Rayleigh number. You can see that they're not too far off just through simple interpolation, with errors being maybe 12% or so. Now, in summary, apologies for the rather short talk, but I'm hoping we can have more discussions about these behaviors. But in summary, we have successfully added the heat equation to this eigenvalue code, which is very versatile and can handle quite extreme parameters with relative ease. And we have developed this large database of critical parameters for onset of convection, which we will make openly available so the community can use it. We have our first round of reviews back from the reviewers, and they seem not too bad. So we'll hope to see this published soon. The possibilities are endless. In the near future, we want to try to find physical insights into the behavior of critical Rayleigh and the critical drift frequency. Why did they behave like this? And as I said, we'll soon make the database only available to everyone. And further down the road, we want to explore, using the same code, we want to explore different, the behavior with Prandtl numbers, different boundary conditions, and internal heating. And then, of course, you can go on to explore magnetic fields, chemical transport, and whatnot. That's all I had to say. I'm happy to answer any questions. And if you have any more, you can email me or follow me on Twitter like some of you already did. Thank you.